This is a pretty fun topic. Okay, so basically, last session, what we covered about is, well, first of all, just to make sure, can everyone hear what I'm saying? Anyone? Yes? Okay, cool. So last review session, we talked about kinetics, which is basically how fast a reaction occurs. This time, in chemical equilibria, we're going to be covering a little bit about how much a reaction occurs. So normally in college chemistry, or when you learn chemistry, you would cover equilibrium after you've learned a little bit about thermodynamics, which is why a reaction occurs. But Ms. Pulick likes to do equilibrium first for some reason, so we'll be learning about equilibrium first. But I will be introducing very slightly some thermodynamic concepts that you'll learn about later. So I guess you guys will be having a bit of a head start than the rest of the class. All right, so I can see that literally everyone is joining as soon as I start. That is okay. But yeah, thank you for participating. All right, let's start with the basics of chemical equilibrium. So I'm aware that most of you are taking Physics 1 or maybe took a physics course before, whether you're a junior or senior. So equilibrium might be a concept that you might be a bit familiar with. For example, and yes, this is, I know this is a chemistry class, so it's kind of weird for me to be talking about physics concepts, but you know, I could go down the rabbit hole of why you should learn physics and chemistry at the same time, but you know, nobody cares and I would just be mumbling. So just to be concise, basically, if you have like a block here, right, then we know from Newton's laws that there would be a gravitational force here and there would be a normal force here, right, from the surface. And since these two forces cancel out, there would be no acceleration. Therefore, we would call this block to be in equilibrium, right? Now, if you don't know any physics, then probably this would also make sense if we had a block here. And if two people were basically pushing on this block with the same force, then this block wouldn't move, correct? And we call that block to be in equilibrium as well. So using the definition of equilibrium by dictionary.com, the most reliable source on the internet, it says a state of rest or balance due to the equal action of opposing forces. That makes sense, you know? I literally just showed you guys two examples of equilibrium, and basically, this block isn't moving. Makes sense? Okay, so there's all kinds of equilibria that we won't be covering today, but the one I just showed you above is called physical equilibria. There's something called thermal equilibria, which is basically where two bodies have the same temperature and therefore no energy is being transferred as heat between the two bodies. That's called thermal equilibrium. But the one that we'll be mainly focusing on today is chemical equilibria, which is basically the condition existing when a chemical reaction and its reverse reaction proceeds at equal rates. Now, there is a trap that a lot of people fall into when we talk about equilibria, and that is, oh, so if a reaction is in equilibrium, does that mean that the reactants and products, that the reaction just stops? And I think I've spoiled the answer to you, but the answer is no. All chemical equilibria are dynamic, and what I mean by dynamic is that, as you can see in this graph here, the forward rate and the reverse rate does not approach zero. It approaches a certain value that is equal, where forward rate and reverse rate becomes equal. So it seems like that the reaction isn't proceeding, or like the reaction composition isn't changing, which is true, but it is untrue to say that the rate of the reaction approaches zero, if that makes sense. So there are key things to, remember when we're talking about equilibrium, but some of them are like, so when a system is at equilibrium, it is in a state where there is no tendency to form products and reactants. That's true. And we can kind of, think about that when we think about the definition of equilibrium itself. All equilibria are dynamic, like I just said. The reaction rate or the forward rate and the reverse rate approaches a certain value, does not approach zero. That's a key thing you should probably remember. And as the reaction proceeds, the reaction rate increases until it matches the forward reaction. That makes sense because when a reaction occurs, then you would be forming products, right? Now, if we recall from our kinetics review session, we remember that when these products collide, they might also have a chance to form the reactants again. And because the concentration of products increases as the reaction occurs, that means there's more probability for these products to collide to become reactants again, right? I'm getting a message. I hate you so much. Okay, so if that makes sense, does anyone have any questions? I'll take that as a no. All right, moving on. So again, chemical equilibria are dynamic, unlike other equilibria such as physical equilibria, which is something you may have heard in physics and something I've just introduced. This one is dynamic, meaning the reaction rates do not approach zero, they approach a certain value. If you're taking notes, you probably should write this down because this is probably one of the most important things that everyone forgets about in equilibrium, and Ms. Pulick will 100% test you on this. All right, so moving on to the equilibrium constant itself. Now, I said that in a reaction that the reaction would basically, the reaction composition will stop changing at a certain point, but not all reactions are created equal, meaning that there are some reactions where it barely reacts at all, and the forward reaction rate and the reverse reaction rate would match when barely any of the reactants has turned into products, or there might be a reaction where it basically essentially goes into completion, which basically means that, well, 100% of the reactants has turned into products. Now, because each reaction has its, hello Josh, welcome back. Because each reaction has its own characteristic equilibrium point, or has a characteristic composition where the forward reaction rate and the reverse reaction rate would match, we give a constant to it. And this is known also as the law of mass action, which for a general reaction like this, then the equilibrium constant will look something like this. My arrow did cover up the equilibrium constant. I'm so sorry about that. But anyways, so for example, if we have a reaction like N2O4, actually, no, let's not use that. No, I'll give an example later. But basically, some things to note about the equilibrium constant. It is a constant, which means that for a given reaction, there will be only one value. Now, there is one exception to this rule, and that is temperature. If you increase the temperature of a reaction, it will affect the equilibrium constant. But besides that, it will always stay constant unless you change the reaction. Okay, any questions? Any questions? No? All right. So, equilibrium and phases. Phases determine what values to use for the equilibrium constant. And this is the general expression for the equilibrium constant and shown. Now, here in my presentation, it uses the terminology known as activities, which is something you most definitely do not need to know for AP chemistry and probably your undergraduate college chemistry course later on. But, nobody really cares. But in my purpose, for example, as you can see, for an ideal gas, now from the previous PowerPoint or presentation, or I'm so sorry, from the previous slide, I use concentrations, right? But we only use concentrations when the phases of the reaction is aqueous. Basically, as you can see here, this reactant A is in aqueous state with a coefficient of lowercase a, right? So we use concentration of A with the lowercase a as the power of the concentration. But when it's an ideal gas, we instead use partial pressures. And like I said earlier, for a dilute solution or an aqueous state, we use the concentration J. Now, if it's a pure solid or liquid, for example, water, which is probably the most simplest example case, we just use 1. We do not use the concentration of water or, for example, iron. Stuff like that, you never put in your equilibrium constant, if that makes sense. So an example I gave you here is for the reaction of dissolving calcium hydroxide, seems like. So if we write this down, then it would be CaOH solid becomes Ca2 plus in aqueous state plus 2OH, right? Now, we know that the reactants go to the bottom and the products go to the, thank you, Josh, CaOH2. We know that the reactants go to the bottom and the activities go to, no, the reactants go to the bottom and the products go to the top. So we put calcium hydroxide, but because this is in a solid state, we would just put 1 here. And then because these two are in an aqueous solution, we would use their concentrations, which is basically calcium 2 plus. And then since it's 2OH, we do OH minus to the second power. Now, always don't forget to add the coefficients because this is probably one of the biggest mistakes that you'll make in your during the test. So don't forget about them. All right. This is great. So a little bit more about the equilibrium constant. First of all, the equilibrium constant is unitless. What I mean by that is that there are no units in equilibrium, despite the fact that, well, let's say using So here's the thing. Remember this, right? In this example, if you put the units here, for example, if we say we had 1 mole of calcium hydroxide and 2 moles of sodium hydroxide, no, of the hydroxide anion, although this isn't really how it works, you'll see that we end up with units that are mole to the cubed, which doesn't make sense because I literally just said 2 minutes ago that equilibrium constant is unitless. And the reason for that is because what actually happens in reality is that, especially, for example, for this calcium ion, when we say concentration, what we do is we have the concentration of calcium ion, right? And then we divide that by the standard concentration, which is basically 1 mole, right? Now, you don't really have to know this, but just in case you're wondering during class why equilibrium constant is unitless, even though there are clearly units here. This is the reason why. Because normally you divide all of the concentrations by the standard concentration, and you divide all the partial pressures by the standard pressure. Now, why do we omit this? It's because it's 1, and anything divided by 1 is anything. So it doesn't, it's kind of, I guess it's kind of annoying to write all of these down every time. So we just tend to omit it. But you always have to realize that it is there technically. Moving on to, okay, so continuing on. I've just shown that the equilibrium constant is unitless. Now, here's the very important thing. If K is smaller than 1, then the reactants are favored in equilibrium. And if K is larger than 1, then products are favored in equilibrium. This also makes sense if we give an example for a reaction where A and B are in equilibrium, then the K would equal A and B if we assume this is an aqueous solution. Excuse me. Now, if this equilibrium constant, let's say, is 100, then we can see that there is 100 times more B than there is in A, meaning there's 100 times more products than there are in reactants. Now, this is sort of a simple case scenario. You won't really see these types of reactions a lot in chemistry, but still gets my point across. For example, another example is if K is equal to 0.01. If K is equal to 0.01, that means there's 100 times more A than there's B, meaning there are 100 times more reactants than there are products. So this is starting to make sense, I hope. Another thing, or another concept that chemists like to use a lot is the reaction quotient. I think I pronounced that wrong, but it is basically characteristic of the composition of the mixture. What does that mean? It basically gives a value that shows what the composition or what state the composition of the reaction is. And where do we use this? We use this often to compare where, I'm so bad at English today. We use it to compare what the composition of the reaction mixture is compared to its equilibrium state. Let me explain that a little bit more. So for example, if we say that at a certain given point of the reaction of A becomes B, if we say that A has 0.03 moles and B has 0.05 moles, then from the reaction quotient, we know that 0.03, 0.05 equals 5/3. And and that's basically what the reaction quotient is. Now, the most important thing and why the reaction quotient is important is because we know that in this state, well, when we use reaction quotient, basically it means that the system isn't in equilibrium yet, but this will become an equilibrium given enough time. For example, for this reaction A and B, if K is equal to 1, while at the moment Q is equal to 5/3, Q will always approach the value of K until the reaction reaches equilibrium where Q is equal to K. And I honestly hope that makes sense. But, oh, and one more thing to note is that unlike the equilibrium constant, which only has one value for a given reaction, but like I said earlier, it may change with temperature. Q can have an infinite kind of, why did I write reactions? An infinite kind of possibilities, basically. So this Q value could be 1000, 1, 0.0001, 69, 4000, stuff like that. Does that make sense? Any questions? Can I move on? Okay, fair enough. Conversion between equilibrium constants. So earlier I mentioned how phases are very important in equilibrium, in expressing equilibrium constants. And as you can see, when we introduce an equilibrium constant in terms of concentrations, we tend to put the subscript C. And in terms of partial pressures, we tend to introduce it in subscript P. Now, why is this important? Because you can't assume that Kc is equal to Kp unless there are actually two case scenarios where they are equal. One, when there aren't any gases involved in the reaction, meaning that if there are no gases released or consumed in the reaction, then you can assume that Kc is equal to Kp. But in that case, you would probably not need to consider Kp in the first place. The second case scenario where Kp is equal to Kc is, well, we can see in this reaction when the change in moles of gas is equal to 0. Now, what do I mean by that? Well, if we give a random reaction like A plus B becomes C plus D, right? And if we say that this is an aqueous state and this is in gas state, right? And this is an aqueous state and this is in gas state, we can see that 1 mole of gas forms 1 mole of gas. That means there is no difference in the moles of gas that is present in this, reaction. And in that case, because this difference is 0, we can really justify that Kp is equal to Kc. So when is Kp and Kc different? Well, using this equation, which can be derived, but it'll be something that we probably cover in later chapters or perhaps even never. K is equal to RT to the power of the difference in number of moles in the reaction that occurs, and then this times Kc. So using this example right here, if we say that 1 mole of gas forms 2 moles of gas as a product, then the difference would be, well, 2 minus 1 equals 1 mole of gas. So we would put 1 here and then calculate this, and then we can see there is indeed a difference, a multiplier difference of RT for Kp. Does that make sense? I'm probably confusing you guys. Any questions? Is the change of moles only for gases? Yes, it is only for gases. All right, moving on. Josh, would you like to do the honors now?
Sure, I would, Kwan. So we can talk about Le Chatelier's principle now. It's one of the most important principles in equilibrium. What it does is it allows you to make really quick, kind of qualitative or intuitive predictions about how a system will react. The main idea is that if you have a system and it's at and you move it away from that equilibrium point, using some kind of stress or change, is going to try and shift back towards equilibrium. It's going to change in some other way so that it gets back to that equilibrium. So that's a result of the equilibrium being like a stable point, or the kind of point that nature aims to get to. Equilibrium is the desired outcome, I guess you could say. And so the main changes that we would be dealing with would be changes in concentration. So you might increase or decrease the concentration of a reactant, or increase and decrease the concentration of a product. And usually that would take the form of either adding in a product or a reactant or removing it from the reaction. You might also change the pressure, and that's just very similar to concentrations, but it is for gases, right? So if you inject some gas into a container, then you will increase the partial pressure of that gas. If you remove gas from the container, the partial pressure decreases. You can change the volume of a container where a reaction is happening, either by increasing or decreasing it, and we'll talk about that later. And you can change the temperature by increasing or decreasing the temperature that the reaction runs at. And again, so the goal of the shift that is dictated by Le Chatelier's principle is that the system wants to return towards equilibrium. Okay, so we can talk about how exactly it works now. So suppose you had some kind of reaction, say like A plus B yields C and D. So what you want to do is, for concentration, you want to think in terms of, is there too much or is there too little? And then you shift to fix that. So if you add A into the mixture, well, there's too much A, right? Because it was at equilibrium, meaning it has, you could say, the right proportion of C, D, A, and B. You add A, now you've got too much A, which is too much reactants. So you need to decrease the amount of reactants, and that's done by shifting to the right towards the products and away from the reactants. Now, if you were to remove A from the system, then you have too little A. So you need to make more A, and you do that by shifting the reaction towards the left, towards the reactants, and away from the products. So pressure, one very important thing to note with pressure is that it is the partial pressures of the gases that are relevant. So you might occasionally see a problem where you're injecting just kind of an unrelated gas into a container. So suppose you have, I don't know, argon and water gas reacting. It doesn't really matter. But then suppose you were to inject neon gas into the container. The total pressure is going to increase, right? Because you're increasing the number of moles of gas inside the container. But that is not going to affect the reaction between water gas and argon gas, because the partial pressures of water gas and argon gases aren't changing. It's just the total pressure. So again, you need to look at the partial pressure. And really, it's very similar for pressure. It's very similar to concentration effects, but it's just for gases instead of aqueous solutions. Changing the volume is a little bit complicated. So what works is, if you increase the volume, then the concentrations of each element that's reacting is going to decrease, right? If you decrease the volume, those are going to increase. And same thing for pressures. If you have gases and you decrease the volume, the pressure is going to increase. If you increase the volume, the pressure is going to decrease. And we have more about this on the next slide, but I'll explain now. What you need to do is you need to look at kind of I would call it the order of the reaction, or of the products and the reactants. So if you have more moles of products, and with more moles of products than moles of reactants, then the order of the products is greater than the order of the reactants, which means that if you increase volume, well, we'll save that for the next slide. Actually, it's easier to explain with the next slide. And also for temperature, I think you guys probably covered this in class, but you just imagine heat as a reactant if the reaction is endothermic, and you imagine it as a product if it's exothermic, and then you can kind of translate it to a concentration problem. So if you input temperature and or if you increase the temperature and it's an endothermic reaction, that's essentially the same as increasing the reactants, which means you need to shift to the right. And same for all the other situations. So it's important to realize that using Le Chatelier's principle is actually just kind of a veiled or a covered way of using the reaction quotient Q. It's less quantitative, but in principle, you're doing the same things. So imagine if we go back to the reactant concentrations, imagine you have A plus B yields C and D again, increasing, say, the concentration of A, that will cause Q to decrease, right? Because you are increasing the denominator of that Q fraction. So now you have Q decreasing, which means Q gets lower than K. And as Kwan was talking about earlier, the system always wants to make Q equal to K. So Q is going to increase, and you can do that by increasing the numerator and decreasing the denominator, which is what happens when the reaction shifts to the right. Again, pressure is just a similar thing, but you would switch out concentration for pressure. So when you increase the volume, the concentration or the pressure is going to decrease. But the amount of products compared to the amount of reactants is what determines how Q changes. So if the order of the numerator increases or is greater than the order of the denominator, then Q is going to have to shift, or is going to decrease, and the reaction is going to have to shift right. If the order of the numerator is less than the order of the denominator, then the reaction is going to have to shift left because Q would be greater than K. And what I mean by the order is the number of moles. So if we had, like, I don't know, 1A plus E yields 3C plus 4D, the order of the products would be 3 plus 4, which is 7. And the order of the reactant be 1 plus 3, which is 4. So in that case, the order of the numerator would be greater than the order of the denominator. Increasing the volume would mean you would have to shift right. And the dependence of Le Chatelier's principle on temperature is a little different. All the other shifts you can kind of boil down to a shift in concentration. Temperature is different. So when temperature changes, Q remains constant, but K is going to change. So the reaction is still going to shift, but now it's for a different reason. Before it was because Q was changing and K was constant. Now Q is constant and K is changing. You don't really need to know all these equations. You can just feast your eyes on them for now. But they might help you to understand it a little bit better. And these equations are the reason why K changes. Okay, and our final topic to cover in the review, solubility product. So the solubility product is just a special case of the equilibrium product for a where dissolve happening. So if you had this compound, A subscript A and B subscript B as a solid dissolving into A A ions and B ions. The solubility product would be just the concentration of A to the 8th power and the concentration of B to the Bth power. Kind of as we talked about before, it's just an equilibrium expression, so don't get too caught up in the terminology of solubility product. And here, as Kwan is writing, an example of this would be iron sulfide dissolving into an iron ion and a sulfide ion. So for that, KSP would be the concentration of the iron ion times the concentration of the sulfide ion. Yeah.
Yeah, sure. So we'll give you guys 2 minutes to do this problem, and hold on, let me set up a poll. There you go. And timer for 2 minutes. Let me get it ready. Starting now. All right, time's up. Josh will explain this question.
Okay, so we can just go through the answer choices one by one. So crushing up the calcium hydroxide into smaller pieces, so that's not really changing the amount or concentration in any way. That would increase the rate of reaction, but increasing the rate of reaction does not change the equilibrium point. So that wouldn't do anything. I guess we can skip to answer choice C, which might give you a hint that B is actually the answer. But if you add calcium oxide, you have to notice here that it's a solid, right? So if you're adding a solids don't factor into shifts. You can see that by looking at the expression for Q. In this case, Q would just be the pressure of the water gas, right? So that is not going to change anything. It's not going to affect Q. It's not going to affect K, so it's not going to shift the reaction in any way. Adding nitrogen gas, again, that's just not really related to the problem. It would change the total pressure of the system, right? But it wouldn't change the partial pressure of the water gas. So it wouldn't be considered a shift or a stressor. For part B, so delta H greater than 0 here, that means that it's endothermic. So heat is a reactant, right? So we can put heat over here. So decreasing the temperature, that's equivalent to taking heat away. That's going to mean it's going to shift to the left, right, to increase the heat. So if it's shifting to the left, the amount of calcium hydroxide is going to increase, while the amounts of calcium oxide and water gas are going to decrease. Does anyone have any questions about that one?
I'll take that as a no. All right, let's move on to question type 2. This is a bit mathy, so we'll give you 3 minutes to try this problem. Hold on, let me clear the poll. There we go. And timer starts now. Seems like it is time. To the 8 people who did not respond, do you guys need more time or? Can you guys see the answer? The answers by any chance? No, right? Okay, cool. Can you fill out the poll again? I'm sorry. I added an I don't know one just for people. Okay. So this is how it looks like at the moment, and it seems like to the 6 people who has answered C, I believe it was 7 earlier, but you are correct. Now, let me briefly explain how to do this problem. Okay, so they give you an equilibrium constant, and they also give you how much, or basically um, how many moles each of the products and reactants have. Now, since a solution contains 0.5 moles each of all 3 of these, we know that from writing this equilibrium constant, we know that, well, first of all, these are reactants, so the concentration would be down here. There are 4 SCM minus, so we do that to the 4th power, and then the concentration of cadmium thiocyanate, like that. Right, and this equals 1.0 times 10 to the 3. Because all 3 of these species are in the same solution, we can say that the volume of the solution is V, correct? And because they're all in the same container and this is an equilibrium, we can say the concentration of all 3 of these species is 0.5, correct? Now, because the concentration of all 3 of these species are the same, well, if we plug this 0.5 over V value in our equation, like this, well, we can see that, interesting. Okay, we can see that these two cancel out, and which gives us basically V over 0.5 to the 4th power equals 1.0 times 10 to the 3rd. Now what I did here is I just made this to negative 4th power, and then I swapped the denominator and the numerator to get this. Now, if we do some simple rearrangement, we should get that volume is equal to 2.8 liters. Any questions? All right, moving on to the 3rd problem. Okay, 3 minutes. All right, time. Let's look at the poll. I'm an idiot. Okay, cool. So, seems like there's an overwhelming amount of D's right now. And the correct answer was D. So, Josh, would you like to explain this or should I? Yeah, sure. Okay. So, this is a typical KSP problem that you will probably see in on the test this week. So, they give you a KSP value of 1.8 times 10 to the negative 7th. It says, what is the maximum fluoride ion concentration possible in a solution? And it gives you the barium concentration. So if we write the KSP equation, which is KSP equals barium, and then F minus to the second power, because, well, if we write down the chemical equation, which is the first thing you should do, and isn't the first thing I did because, well, I'm bad. You have the barium ion here with 2 fluoride ions, and we can see that this will give this. And this is equal to 1.8 times 10 to the negative 7th. Now, if we rearrange this, we can get that fluoride ion equals the KSP over the barium concentration, and then square root that, which gives you 1.9 times 10 to the negative second moles. Any questions? Okay, moving on to question 4. We'll give you 2 minutes for this question. And that is time.
Okay, so for this question, never mind. We may be having some technical difficulties.
No, we're not. I just want to give you guys a little bit more time since most people didn't respond yet. Sorry about that, Josh.
Okay, so for this one, the answer actually was A, and it looks like it was a little bit more difficult, so we can go over it. Um, so first thing to do would probably just be to write out the chemical equation. And Quan, if you could do that up at the top. Um, so it looks like the cobalt and water compounds is reacting with some chloride to form a compound of cobalt and chloride ions. So that is going to look like that. Okay, so we'll go through the shifts one by one. And actually, let's start with the second one. So when Ag is added, when silver is added, the solution turns back to pink. So you guys should probably know that when or that AgCl, silver chloride, is insoluble, right? So if you're Ag to the solution, that's going to react with the chloride ions and pull those out of solution. So essentially, adding Ag is going to decrease the amount of reactants, which means the reaction is going to have to shift to the left, increase the concentration of the cobalt and water compounds. And so what it's saying is when you increase the concentration of cobalt and water compounds, the solution is becoming more pink. So what that means is the cobalt water compound is pink. And then I guess from that you can guess that the cobalt chloride compound is blue because that's the other color. And then the first clue says when the solution is heated, it turns blue. So that means when the solution is heated, it shifts right. That must mean that heat is a reactant, which means that the reaction is endothermic. So one is true because the water compound is in fact pink, as we talked about. Part two is not true because as we just showed, formation of the chloride compound is actually endothermic. So A has to be the answer.
Yeah.
Oh, any questions?
Any questions? All right. I guess we can move on to the next question, which is this one. We'll be giving 2 minutes for this problem. Starting now. is time. There you go. Josh will
Okay.
explain it again. I'm so sorry. There you go.
So this one went quite a lot better, and I guess it's a lot simpler. So we can just start from the bottom of the options and work up. So option D says the reaction is not at equilibrium because the position molecules are still changing. It's true that the positions of molecules are changing, but it's a dynamic equilibrium, so the molecules can move around and reactions still can occur. So D is not completely true, so we can strike that one out. C is not at equilibrium because the concentrations of A and B are not equal. Well, the concentrations of A and B don't have to be equal for the reaction to be at equilibrium. If you remember back at the beginning, Kwan had a slide with a graph that like this. Just draw it with my mouse quickly. So he said that once these curves flattened out, then the reaction was at equilibrium. Well, the concentrations are not equal. That's just not a condition of equilibrium. So D are both out of the running. The reaction is not at equilibrium because all of the A has been consumed. Again, that's just false. In most reactions, some of the reactant will remain. In all reactions, at least some minuscule tiny amount will remain. So B is false, leaving only A. Oh, that's true because one of the definitions of equilibrium is that the concentrations of the reactants and products are not changing even if reactions are still occurring. That's just what it's supposed to be a dynamic equilibrium. So A is the correct answer here.
Any questions? Oh, it seems like everyone answered this question correctly. That's very cool. All right. Moving on. We have 6 questions left, including this one. So, we'll give about 1 minute for this question. About 10 seconds more. All right. Josh, would you like to explain this time again, or should I? You can? Okay, sure, cool. So the question asks, for which of the following reactions would yield of products at equilibrium not increase at a higher pressure? All right. Now, basically, to answer this question, you have to ask yourself, well, which one either has the same amount of gas molecules in the reactants and products, or just does not contain gases in the reaction itself. And you can see over here from A that there are 2 molecules of gas molecules in the reactants, and there are 2 molecules of product gas molecules in the products. That was a terrible sentence, but we can see that these two match. So even if we increase or decrease pressure, because there are the same amount of gas molecules, we can predict that the products at equilibrium would not increase at all. So we know the answer is A. Now let's take a look at the other answers. So for B, we can see that there are two gas molecules in the reactants, and there's one gas molecules in the products. So we can see that if we increase pressure, then due to Le Chatelier's principle, we expect that the reaction rate, the forward reaction rate would increase compared to the reverse reaction rate. And it's basically the same case scenario for C and D. We can see 4 here, 3 here, and then 5 here, and 2 here. Any questions? All right, moving on to question 7. We'll give about 2 minutes for this question. Oh, actually, changed my mind. We'll give 1 minute for this question. Yes, it is time. Josh will explain this question for you guys. There you go.
Okay, so it looks like most people got the right answer, which is cool. So the problem says at 400 degrees Kelvin, this reaction has a Kp of 8.2 times 10 to the negative 4. And this reaction here is from, this is a pressure or a gas phase reaction, and it's talking about Kp. So we would write it in terms of the pressures, the partial pressures of the gases. And here, Kwan has written the K expression up at the top using the equilibrium, or using the reaction coefficients as exponents. So you can see here, the exponent of PO2 is 1/2. So they don't actually always have to be integers, just so you know. It's perfectly valid for them to be fractions. And here, Kwan is writing the Kp of the other reaction. And so what you might notice, if you look hard, is that this is actually the first K value squared, right? Because square PSO2, you get PSO2 squared, which is in Kp2. Square PO2 to the 1/2 power, and you get PO2, say PSO3 at the bottom. So KP2 is just KP1 squared. If you plug in the value of KP1 as 8.2 times 10 to the negative fourth, you will get A. And you could do that with mental math pretty quickly, because 8 times 10 to the negative fourth squared would be 64 times 10 to the negative eighth, which is pretty much A.
Any questions? Any questions? I will assume no. All right, moving on to 21. We talk. Ooh, okay. I'll give 3 minutes for this question. Feel free to take your time. So, something to point out, especially for the equilibrium constant, um, for the last question, I did mention that the equilibrium constant value doesn't change besides temperature. Now, in this case, it might be wiser to just, although it is the same reaction, if it confuses you too much, you can just assume like if they have different multiples of coefficients, just treat it as a different reaction. But yeah. It has been 3 minutes, but seeing that 7 people haven't responded yet, I'll give more time. Does anyone need more time, or should we start? All right. So I'll explain this one. So I think this is probably one of the best practical applications of KSP, and that's figuring out how much solid, or not solid, but how much salt would dissolve in water. And in this case, the salt given here is silver chloride. Now, the question asks what mass of silver chloride, mass, not concentration, what mass of silver chloride will dissolve in 1 liter of water? And they give you the KSP value, which is 1.8 times 10 to the negative 10th. All right, so let's write down the equation first of all, which is AgCl solid turns into Ag plus in aqueous solution, in aqueous state, and in chloride ion, like that. Cool. So we know that this KSP equation is going to be Ag plus and Cl minus, like this. Now, it asks for what mass of silver chloride will dissolve. Okay, now we know that, for example, like, this is very theoretical, but ignoring the equilibrium constant, we know that if 0.5 grams of silver chloride were to dissolve, then the moles from the 0.5 grams would be equal for both silver ion and chloride ion, if that makes sense. So basically, if there was 0.5 moles of silver chloride here, then there would be 0.5 moles. And if we were to assume theoretically that they were to all dissolve, then there would be 0.5 moles of Ag plus and 0.5 moles of chloride ion, if that makes sense. So basically, if we assume the concentration of Ag plus to be X, right? That would X would also be represented of the concentration of chloride ion. Therefore, we can say that this is X squared. Now, then we can say that X is equal to the square root of KSP. Now, this X happens to be in moles. So what do? We multiply, we use the molar mass given. If we multiply the square root of KSP by the molar mass, and since it asks for in milligrams, if we multiply 1 gram and then 1,000 milligram, like that, we get our answer. Let me plug into my calculator. It says 1,000 times the molar mass, 143.4. If you're confused why I did the conversions from milligram to gram, it's because molar mass is represented in grams per mole. So multiply that by square root of KSP, which is 1.8 times 10 to the negative 10th. I get 1.92 milligrams. So the answer is B. Any questions?
Wait, do you guys know ice tables yet?
No, they don't. You learned that in weak acid, weak base. Oh, do you?
Yeah. Yeah.
My bad.
So Kwan was just explaining like the theory behind the ice tables. But if you guys are more familiar with them, you just write like the initial 0 change plus X for both Ag and C. So at equilibrium both X, and then you find square root of KSB. Like,
Wait, is my internet connection dying? Oh, okay. Sorry. I didn't. Well, for solubility product, I think it's using the ice table might get a bit annoying, but yes. All right. Moving on to question 9. I'll give you 2 minutes for this question. All right. So Josh will explain this question.
okay, so we'll go through it step by step. So it says it's endothermic, which means we can have heat as a reactant, right? So we have heat over here on the left. So increasing the temperature, that would be equivalent to like inputting a reactant. It's going to shift the equilibrium to the right, which means it would increase the amount of this PCl5, which is what we want to do. So that's good. For 2, Kwan, if you could write it KS or the suppose we doubled the volume, right? Then the of each thing is going to go or be in half, right? If you double volume, pressure is going to divide in half. So we have Q would be you would divide thing by 2, each P term by 2, right? If you simplify that, that Q equals 2K. So greater than, that means increasing the volume pushes it past it. And you would need to go back towards the reactants, right? You need to shift left to fix that. Increase the concentration 5, so 2 would not work. Answer is A.
Yay. All right. So moving, I think my internet is dying a bit, but moving on to another question. We'll just do one more question after this. Okay, goodbye, Josh. So I'll give you 2 minutes. I've opened the poll. Do you guys need more time or? Um, if nobody needs more time, should I start or? Ooh, smiley face. Okay. I'll take that as a yes, I guess. All right. Well, just for the sake of time, I'll start explaining now. Basically, as we can see, it seems like our answer choices are a bit divided, but So the first thing we want to do is, well, it's given in milligrams, and nobody really likes milligrams, so I would convert this into grams, which is 6.7 times 10 to the negative 4 grams per liter. Now, we know that when we use KSP, we often use moles per liter, not grams per liter. So what we want to do is convert this into moles per liter. And we get 128.1 grams equals 1 mole. Now, just to briefly explain why this works. It says that 0.67 milligrams dissolves in 1 liter of water, right? And 0.67 milligrams in this case refers to calcium oxalate as a whole. But if we use its molar mass, then we can calculate the number of moles of calcium oxalate that was dissolved. And like I said earlier, we know that, well, the number of calcium oxalate, the number of moles that is dissolved by calcium of, oh my God, I can't speak English today. So the number of moles that is dissolved is equal to the number of moles of the ions that is released from being dissolved. I'm so sorry if I confused you there. But anyways, if we calculate this, we should get something like, seems like 5.23 times 10 to the negative 6 molarity. Okay. And because this is essentially the concentration of the calcium ions and the concentration of our C2O42 minus, or what we call oxalate anions. Remember how I made the relationship where KSP equals x squared? This value is the same thing as x in this case. So if we square this value, we would get the KSP value. And that turns out to be 2.7 times 10 to the negative 11th power, which is C. Any questions? Moving on to our last question, question 31. I'll give you guys 2 minutes and we can have a 10-minute early release. I've cleared the answer choices. Does anyone need more time, or should I start explaining? If you need time, can you type in the chat? All right, so let me explain this question. It seems like our answer choices is slightly divided, but the correct answer was B. Let me explain briefly why. So the first thing we want to do is we're given the equation, we want to write the equilibrium constant, but we can see that there are two species that are solids, calcium carbonate and calcium oxide, so they won't be present in the equilibrium constant, meaning this this is not correct. The correct one would be, since this is a gas species, only carbon dioxide would be present. So the equilibrium constant is actually equal to the partial pressure of carbon dioxide, meaning that even if we increase the amount of calcium carbonate that is added as a reactant, that means the partial pressure of carbon dioxide will not be changed as a result. Therefore, the answer is B. All right, any questions? Any final questions, regardless of what we're doing right now? All right, then you're free to go. Thank you for participating. I definitely enjoyed this much more than I expected. If you have any questions, feel free to ask me privately or after everyone leaves. But yeah, thanks, guys.